Okay, hello everyone, good morning and welcome to today's seminar, which is a system approach to UVC LED-based disinfection, which is being brought to you in association with the CHIA. My name is Ray Maloney. I'm the editor of Lux Review and I'm going to be your host for the next couple of hours. First of all, a few housekeeping points. Now, in your control panel, you have a list of options there and you should be able to see a questions tab. So feel free at any point today to pop your question to the speakers here at any time, and we'll get them answered when all the speakers have completed today. So just put your questions there. Now, if you want your question directed at a particular speaker, please say so. Please make that clear in your question. Now, any questions that we don't get around to today, we'll circulate to our speakers over the next 48 hours. So hopefully we'll get an answer to every single question. Now, if you're having technical difficulties or if there's any question or comment that's not related to the topic in UVC disinfection lighting, please use the chat box instead. Now, my colleague Charlie will be monitoring this and she'll be able to assist you with any difficulties you may be having. So, as I say, keep everything about the topic questions in the questions box and everything else in the chat box. Today's event is being recorded and we're going to share that link to the recording with you in an email, and you should get that about roughly an hour after the end of the event. Now, this morning's webinar presents a complete story about UVC, and we're really grateful to the CHIA for bringing such a stellar lineup of speakers to the table today. The webinar looks at the science behind UVC lighting LED technologies, the LEDs from the CHIA driving solutions forward, how optics and module manufacturers are successfully integrating UVC LEDs into products, and how specific real-world projects are implementing these solutions. Now, we couldn't cram all this and the Q&A into an hour, so today's webinar is going to be between an hour 15, hour 30, something like that. So we'll see how we get on. Now, our first speaker this morning, delivering the keynote presentation, is Thomas Westerhoff. He's the Deputy Group Manager Embedded Systems at the world-renowned Fraunhofer Institute. He's going to compare dosages of mercury and LED and look at some extremely interesting applications. Following him will be Jonathan Klee. He's the UV LED Account Manager at CHIA. He'll look at UVC LED technology at the heart of the discussion, as well as applications and markets. Next, we have Tero Makinen. He's the Business Development Manager at the leading optics specialist Ledl, and he will introduce a very interesting optical first. I won't steal his thunder on that, so keep an eye out for that. And following Tero is Peter Sonnenschein. He's the head of sales at LED module manufacturer Lumatronics, and he will reveal the results of irradiation simulations on the disinfection of surfaces. And he's joined by his colleague, the application engineer Mario Rose. And last, but certainly not least, is Thomas Efson. He's the managing director at UV solution provider Efson, and he'll share some interesting disinfection data across pathogens. So that's our really interesting lineup for this morning. Without further ado, I'm going to hand over to Thomas Westerhoff of the Fraunhofer Institute, and I'll rejoin you for our Q&A sessions in about an hour. Thomas.
Yes. Good morning, everyone. Can you see my screen? Yes. Yes, good morning, everyone. My name is Thomas Westerhoff, and I want to talk about advantages of UVC LEDs. And with these advantages, there are opportunities for new disinfection applications. But let's start with some UVC disinfection basics. The photon energy of UVC radiation is very high, and therefore it is able to split chemical bonds in the nucleic acids of the DNA, which after that are reformed as so-called thymine dimers, and therefore DNA is unable to be duplicated during the cell division process. This DNA damage is dependent on the emission wavelength of your radiation source, and the acting dose or fluence in joule per square meters. Different pathogens also have different sensitivity of UVC. You can see E. coli is a microorganism that is very easily to inactivate. You only need 60 joules per square meters for 99.99% inactivation. And on the other side, you have molds or spore formers like Aspergillus niger, which needs about 5,000 joules per square meters for this inactivation rate. Yes, maybe I have to talk about the terminology. We talk about germ reduction if you are less than 99.99%. Disinfection is at least 99.99% of inactivation. Sterilization, you will need 99.999% of inactivation. But there is an opponent of UVC radiation, and it's a process called photoreactivation, which is caused by light from 300 to 500 nanometers. This is UVB radiation, or UVA up to blue, and this activates the photolyase, which can be able to repair the damage you got with UVC. You can see here in this diagram some microorganisms. The violet one is without photoreactivation, and you see if you have photoreactivation processes, for instance in air disinfection where you have sunlight presence, you need more radiation dose. We assume that 400 joule per square meter is a good value to be safe in the UVC for a 4-log inactivation. But disinfection is also possible with UVA. You will find some systems on the market, but you will need very, very high doses. They can be up to 100 times higher than in UVC. If you use UVA, like 390 nanometers LEDs, or you use photocatalysts to produce radicals. Now let's talk about the advantages of UVC LEDs. As you can see in the diagram, the best performance in inactivation of microorganisms is about a range between 260 and 275 nanometers. There are different microorganisms with different maximas, and the yellow diagram is the emission spectrum of a mercury low pressure lamp. You will see it's a very narrow band emission, which is not in the optimum wavelength, and you will see an UVC LED, which has a very wide spectrum. You will cover more wavelengths, and you also have in this spectrum wavelengths which are near the maximum of disinfection efficiency, and therefore LEDs commonly gives you better disinfection results. Another point is, an advantage is that UVC LEDs are completely ozone free because they have no wavelengths that are lower than 240 nanometers. If you are below 240 nanometers, you will produce ozone, which is an irritant gas, and you don't want it. Let's look at this example, which are the inactivation of Bacillus subtilis spores. And if you look, for instance, at a fluence of 30 millijoule per square centimeter, you will only have an inactivation rate of 1.5 log. If you use a 269 nanometer LED, you will have 2 log steps better disinfection with the same radiation energy, and other LEDs like 280 nanometers and 255 are in between of this. So with an UVC LED with 269 nanometers, you are very close to the disinfection limit. Here we have in comparison of a 54 nanometer lamp and a 266 nanometer LED for 3 other species. The E. coli, you will see the LED is much better, and Salmonella, it is even more better, and the best performance you will get on Listeria. The third advantage of UVC LED is that there are very small spot emitters, very spotlights, and you can arrange completely freely in different configurations. You can use it on flat square panels, round panels. You can combine different LED wavelengths in one. In one panel, you can build line arrays. And of course, you can completely, or you can build completely new arrays like this one, which is where the LEDs are placed on a flex PCB, which is glued into a cooling device. And so you can create optimized radiation geometries for your specific disinfection problem. The third advantage of UVC LEDs is that they produce very high irradiation intensities because they are very small. Typically, you have chips with about 1 square millimeters, and if you imagine this 1 square millimeters has an UV output of about 500 milliwatt, you could theoretically get a 5 watt per square centimeter irradiation energy. LEDs can be, if you have an appropriate cooling, can be packed very dense on your array, and you can use reflectors or lenses for beam shaping, and so you can focus the radiation energy, for instance, on your surface you want to disinfect. And this will make LEDs well suited for close and short-term surface disinfection. Oh, there is a problem in my diagram. Okay, there's some shifted. What you see here is the heating up curve of a typical low pressure lamp. You will see you will need at least 3 minutes to get the maximum power. And here we have lamps in water, so you have cooling effects that drop and the power drops. With LEDs, you don't have this effects. Full power is immediately available, so LEDs are suitable for clocked operation. For instance, in the faucet, you can open it, water flows out, LED is switched on, and if you close it, LED is switched off immediately. Also, LEDs can be pulsed for a little bit higher output, and you will get less temperature. And of course, LEDs are completely from 0 to 100% dimmable. This makes or gives you the possibility to use them in applications where you need a variable intensity, for instance, in respirator masks, where you can control the LED intensity about the brief across the breath cycle. LEDs are waterproof and shockproof. We have here some tests done with LEDs in a polyurethane, which is tested in water. With this, you can use water as a coolant to get higher output of your LED. But our latest research is to coat them with a 20 micrometer thick layer of polylanes. They are electrical, very high isolating, makes it waterproof up to 60 bar. And we also tested LEDs up to 70 Gs for shockproof, but this is depending on the package type. As you can see, we have here a LED strip on an aluminum PCB with a pyrylane coating. You have to mask out, of course, the LED lens, because pyrylane are intransparent in UVC. but you can get the optimum cooling effect like this, for instance, water disinfection. Well, in summary, we have here a comparison of all the advantages and disadvantages. Of course, classical mercury lamps have also advantages. They are very inexpensive, proven for a very long time. They are on market more than 100 years, and you will find many suppliers. But as I said, they contain mercury, which is harmful for the environment. You have this long heating phase, and they are very fragile. You always have the risk of glass breakage, which makes them problematic if you use them in mobile applications. And of course, you have only fixed emission wavelengths, so you can't use the better performance on other wavelengths. And of course, you are restricted in the geometry because most of them are glass tubes and they are not dimmable. And with this, I'm at the end of my presentation. If you want to see some applications, we can do this in the Q&A section, and I like to hand over to Jonathan Klee.
Yeah, good morning, everybody. Hello, welcome also from my side to today's webinar. Thank you, Mr. Westerhoff, for the nice presentation. I will take the part of the LED manufacturer today, telling you a little bit more about where we are in terms of UVC technology, what we can achieve today, where we want to move, and some general market and some more general information. With that said, I want to start saying some brief words about Nichia. Nichia is a Japanese company founded in 1956 in Tokushima, Japan. It's a family-owned company still, also with having almost 10,000 employees. Nichia started producing calcium powder for the pharma industry, later on going to phosphorus, over to green and blue LED, and later on combining this phosphor, making the first white LED in the market. And today optical semiconductor is a very strong focus of us, and next year we will celebrate our 65th anniversary. That said, I want to straight move into our UV LED section. As you can see, we have a very wide portfolio, mostly covering the UVA area, because this has just been longer on the market for the curing industry, non-destructive material control and applications like that. But also, as you can see on the bottom left, we are moving strongly in the UVC market, currently having two products. One is focusing on the sterilization and disinfection market with more higher power, and one is designed for like more sensing applications with a little bit lower output power. But as you may ask yourself, like, what is the target applications that we see for the UVC LED market? Well, it's basically spread into four parts, which one big part is the surface disinfection. We see a high number of requests these days. I think also highly referring to the pandemic we are facing at the moment. Also, Mr. Westerhoff in his presentation showed some nice examples of it. And LEDs can, with its advantages, just bring a strong benefit there. Then we have the HVAC. This is the classic air purification, which you can find in like public transportation, offices, but as well as in every environment where kind of air filtering, air disinfection is a thing. Then we have the biggest potential for the LED, which is the water market. It has a global necessity. A lot of people still don't have access to like clean drinking water. And of course, the LED is not there that you can replace like several thousand of watts of a mercury lamp with an LED. But if you think around, there's new developments, new ideas coming up to make the LED work for water disinfection. And then we have the biomedical area. This is going into like hospitals, laboratories, stuff like that, where you have some disinfection task or even some sensing task. Our roadmap is looking like that. It's a very brief view because we couldn't share the full here, but I think the point is clear that we have this product today with the 70 and the 17 milliwatt, but we have a lot to come. We recently got the first information about the super high power 4-in-1 package, which we already have. We have the rough specifications. We unfortunately cannot share it today, but after the webinar, if you come to us, yeah, we can definitely talk about that. And as you see on the right, we also plan to develop our smaller sized package in a way that we will offer a wider product portfolio for more application. Diving into our main product for disinfection at the moment, which comes with a peak wavelength of 280 nanometers. It has, or it's specified with 70 milliwatt at 350 milliamps, but because we are delivering such a high quality, high reliability, you can also drive it up with up to 500 milliamps, achieving 100 milliwatt approximately out of one LED chip, which is quite impressive at that stage. Also, in terms of efficiency, we are at around 3.6%. However, this is world leading at the moment. There is no company in the world can do efficiency in UVC like that. And a special feature that this LED also has is it has an hermetic shield. Why this is important, I want to explain on the next slide. So, if you are using LEDs in rough environments, which definitely can happen, especially when you're talking about LEDs for disinfection purposes, it may be that the LED will be affected by some kind of moisture or gases which are going on in the environment, maybe some condensating water, whatever. And this hermetic shield just protects the LED and the dye itself from getting in touch with those substances. And this is very, very important and a very good feature to have on board. What this means in terms of lifetime, you can see over here, we really did a test where we put a very high ambient temperature of 60 degrees and the humidity of 90%. This is not the best environment for an LED. Usually they like it a little bit cooler and with less humidity, but as you can see, still with the hermetic shield, we tested almost 10,000 hours and it's still above 80% under this rough conditions. And as you can also see, the LED without the shield, it just drops down dramatically at a certain point. Here it's at about 6,000 hours, but it can also happen after 1, 2, 3,000 hours. It totally depends on the environment, and you are very well protected using a hermetic shield LED. Now, one of the key questions we are always facing is why Nichia chose 280 nanometer. A lower wavelengths would be more efficient in terms of sterilization. Yes, we fully agree on that. As you can see on the left, there is the DNA absorption maximum. Mr. Westerhoff also referred to that. But we just decided to go for the best overall package. So at 280 nanometers, you have a lower sterilization efficiency, but on the other hand, we have a much more reliable LED in terms of output power, reliability, the heat this LED generates, in comparison to, for example, a 265 nanometer LED. So we chose a random LED from the market with a lower wavelengths, and as you can see on the right, just testing the initial reliability, you can see a more drastic drop down from the 265 nanometer LED than our 280 nanometer LED. So we chose the best package, and in the future, if we are possible to project our current quality and reliability to a lower wavelengths, we will do so. But at the moment, we are focusing on offering you a product which you can buy today, which is a mass production and which we can deliver in constant quality. So how can we prove that our 280 nanometers are working for disinfection? Well, I don't want to go too much about this slide, but this should give you a rough idea of what our LED is able to do, and also it proves that it works for disinfection, even though we don't hitting like the lower wavelengths. This is of course just a rough estimation which you can use because this was tested under laboratory condition with one LED shining on a Petri dish. But in the end, you can use it to like start up your development of your product. just having some reference in your hand. And with that said, I want to come to my last slide, which I call to action, and summarize a little bit. So first of all, we think that today LEDs can already bring a great value to your application when you are not trying to just simply replace a mercury lamp. There's so much more opportunities out there which can be taken because of the form factor, the no mercury, the on and off advantage, etc. So you can today benefit from the LED's advantage in the UVC area, finding new applications, and the replacement process will come later on for sure. Secondly, especially in UVC area where you have like invincible rays you cannot see, it's a very sensitive topic. It's highly recommended to take the chance to talk to all the players in this market, even if it's research institutes, system integrators, certification companies, etc., to just make sure you have a close contact and you can be successful in your development. I think today's webinar kind of shows that, because we have many players out of that chain here today. Yeah, then of course you also need to consider that it's not just the output power of the LED which makes a system efficient. So if you, for example, have a water reactor, it's about the flow geometry, it's about the dosage, it's about the reflection inside the reactor, etc. So there's much more to consider than just having the output power of the LED. And last but not least, I want to say that you can engage and to certain like UV consortiums which are highly focused. They have all the players there, they can help you with your development, and it's definitely worth it to reach out for them. And please make sure to implement the necessary safety requirements when you are using UVC LED. And with that said, I want to thank you and head over to Mr. Taro from Lidl. Taro, it's your turn.
Thank you, Jonathan. And let's get started. So hello, everybody. Also on my behalf, my name is Tero Mäkinen and I work as a business development manager in this company called Lidl. And we are entirely focused on creating optics. And recently we have released world's first optic family, which is specifically designed for the UVC application. And
Jonathan.
Yeah. Pardon?
Jonathan, you could make your screen a bit bigger, your slides.
Sorry.
You just need to go full screen, Tero.
I'm already on full screen.
That's fine now. That's good, Tero.
Okay.
I think
So you're seeing just the presentation slide, not the presenter.
The presentator mode.
Presentator.
Yes.
Oh, okay. So I need to swap. So you are now seeing just my slide.
Perfect.
Perfect. Okay. Sorry about that. Somehow when we tested it worked different way. Okay. Yeah. Sorry about that. Technology is like this. Sometimes it surprises you. So yes, we have recently released this a new optic family, Violet, which is specifically designed for the UVC LEDs. And what is so special about it is the materials we are using. Quite many UVC optics previously have been made using quartz glass, which is having a good transmission, but since it's a glass material, you are limited with a way you can design it and what kind of shapes you can achieve using a glass. Here we are using injection molding technology, and since we are dealing with elastomeric materials, we are having absolutely no limitation at all on the shapes we can achieve. And the silicone material has a very high UV transmittance comparable to most of the other optical materials. And and it's also very resistant to the UVC. The lens itself is held in place with the stainless steel frame, so all of the materials can withstand long-term UVC use. And we have now 3 beams available, ranging from 14-degree real spot beam all the way to 60-degree wider beam. Why do you want to use optics at all in the UVC application? Is because you want to conserve the energy. One of the biggest benefits of the optics is that it allows you to really focus the light, or in this case irradiation, into your application. You can use optics to shape the energy emitted by LED and then put it in your application into areas where it's needed. Like we are seeing here, we have a comparison of 2 cases. We have same 9 luminaires mounted in the ceiling, each luminaire consisting of 4 modules. And on the right, we have the results with the LEDs alone. And then on the left, we have results with the luminaires using these optics. And we can see the benefits we can gain by focusing that irradiation in the places where it's needed, such as in this case, we want to focus the light in this tray area here, this 3 by 3 meter area. And with the LEDs alone, we can achieve on this work plane close to 120 milliwatts per square meter irradiance levels. If we compare to the irradiance levels we are seeing with the optics, we are over twice the intensity compared to bare LEDs. So by focusing the irradiation into this work plane, we can achieve in practice half the disinfection time of the bare LED, or we can reduce the number of the LEDs. So this gives you a lot of tools to optimize your luminaire in a different way. Another application I want to brief touch is upper air UVGI, which is a really big application in the North America. The upper air UVGI basically means the disinfection which is happening in the upper parts of the room, and this room can actually have people in the same room at the same time when the UVC irradiation is being applied. And the way we can do this upper room germicidal inactivation is we need to make sure and focus the light and make sure that it stays in this upper portion of the room where we don't have any humans. And there are limits on the amount of UVC irradiation that you can UVC dose that you can have in these kind of applications. The maximum safe result for the rooms, the maximum safe level of this eye level exposure for the 8-hour exposure time is 0.4 microwatts per square centimeter. And if you look at the results here, our maximum in this application is 0.3. Because again, we are using these violet RS lenses with that 14-degree beam to focus the irradiation in the upper part of the room and making sure that it's staying there in this application. So this is a solution that you can integrate into existing office lighting luminaires, for example, and I would say a new and somewhat disruptive way of disinfecting your office space. So with these couple of examples, I'd like to thank you on my behalf and pass the presentation forward to Peter and Mario from Lumitronics. Thank you.
Thanks, Tero. Hi, everyone. So Yeah, my name is Peter Sonnenschein. Here with me is my colleague Mario Rose. And what we did is we combined the LED optics with the Nichia LEDs into one of our modules. And with this module, we did a concept for a room disinfection that we developed especially for this webinar. But let me say a few words about Lumitronics first. We are an LED specialist from the very beginning, which means we have never done anything else but to work with LEDs. We are a distributor for Nichia since 2011, as well as a distributor for LED. And we have our own software and hardware development department in-house, as well as our own production facilities for the assembly for both flexible and rigid PCB boards. So this is our UVC module Violet. We actually have 3 different versions of this module. One is just the plain module. Another one is the module with Nichia LEDs on it, the LED optic on it, and a small housing. And this particular one, the one I already showed, also has our Lumitronics power controller V2 built in for our security concept. So when Nichia first published their new NCSU 334B series with a significant increase of optical power, we gave ourselves a challenge if we can actually disinfect a whole room by using our modules in a sustainable and secure way. And we asked ourselves, what are the advantages for using UVC technology and not using common UV technology? We already heard some of the advantages for LEDs, so I will keep that short. Let me just add that with LEDs, we have the opportunity to dose the electric power to an absolute minimum, which makes it perfect for battery-driven applications. We also have, with our modules, we have the opportunity to use a software-based security system with our power controllers, which is a great benefit. And because the optical power is not as high as with common UV technology, we will cause less damage for exposed surfaces. It's not only me saying that, but UV Solutions magazine actually published a report at the beginning of this year saying how important it is to balance the UV energy for, on the one hand, needed for disinfection, but on the other hand, to cause damage to exposed surfaces. They did some research in medical facilities and found out that some of the exposed materials like white PMMA actually showed significant damage. So coming to our room concept, the simulation that we did, the room is supposed to be a doctor's office. It has a length of 4 meters, a width of 5 meters, and a height of 2.5 meters. We put 4 of our modules across the ceiling, and we put some furniture in it, an instrument table, which is number 1, a treatment couch, which is number 2, a desk, which is number 3, and a cupboard, which is number 4. As you can already see in this picture, we do have some areas with shadow. And we didn't even put a desktop PC, a laptop, books, plants, or whatever on the surfaces yet. It's just the plain surfaces, but still we have shadow, and this is always bad because when there's shadow, no disinfection can happen. And you can also see that some of the surfaces are not as good covered by the UV light as others. So the question was, how much optical power actually reaches the surface and how long does it take to inactivate viruses and germs? To investigate that, the first step for us was to ask LED to do an optical simulation for us. And the second step will then be to do a test in real conditions. The simulations that we got from LED showed very different values in milliwatt per square meter. The cupboard and the desk showed really low numbers, but the treatment couch and the instrument table showed quite good results. Obviously, we considered the treatment couch and the instrument table to be the most important surfaces, as these ones are the ones that are most likely in touch with patients. But also, the simulation showed that there's still room of improvement in the setup between placing the light source and placing the furniture. With the simulation that we got from LED, we did our calculations for both for SARS-CoV-2 and for E. coli. And you can see what we saw in the previous pictures before. The results for the treatment couch and instrument table are really good, with 12 minutes and 20 minutes for SARS-CoV-2. We chose a dosage of 99.9% because we think this is already a good result. And because of all the shadowing I was talking about in the last slide, we don't expect it to be a perfect result anyway. But also the desk and the cupboard, which are not as good in this setup with the light source, show a way longer time for irradiation. So, coming to our conclusion for our concept, based on the simulation that we did, and I have to say these are simulated numbers, we didn't include any shadowing or temperature or humidity or whatsoever. But based on the simulation that we did, we can say that germs like E. coli can be cleaned on the simulated surfaces within 6 and 59 minutes. A virus like SARS-CoV-2 can be cleaned on the simulated surfaces within 12 and 120 minutes. A real disinfection or inactivation can actually be done overnight or during the day when the room is empty, which is also not that unlikely because doctors usually change the room after a treatment. We saw how crucial it is to have a good setup, placing the light source and placing the furniture in order to have a very good coverage of all the surfaces. But also we saw how important it is to place the light source right above the most important surfaces. We saw that UVC modules, UVC LEDs are a ready-to-use solution for disinfection right now, but we think it can only be a complementary system with other solutions. So it will still be necessary to clean the surfaces with a disinfection spray every once in a while. But if you combine the different solutions, you will have a very secure environment then. With 4 times 23 watts and no use of mercury at all, we consider our solutions to be both sustainable and environmentally friendly. And we have our security system that ensures that nobody will be harmed by UV exposure. And how this security system works, my colleague Mario will now fill you in on that.
Yes, thank you, Peter. Now, to ensure safe usage of our UV modules in the simulated setup, we came up with a 3-layer safety concept that consists of a motion sensor that is placed inside the room to make sure that there is no movement inside of the room, and also a button that is connected to the door to have a feedback of whether the door is open or closed. Another button is placed outside of the room to turn on the system manually. This can only happen if conditions 1 and 2 are satisfied. So there has been no motion detected for a certain amount of time and the door is closed. While the UVC LEDs are turned on and one of conditions 1 or 2 become no longer satisfied, the system is turned off instantly. To represent the system state, we introduced 3 status LEDs, red, green, and blue. The first state represented by the red status LED is the not ready state. Here the system is in a state where it is not ready to activate the UVC module, so the preliminary conditions, motion sensor and door are not satisfied, so there has been either a motion or the door is open or both. When these 2 conditions become satisfied, we move on to the next state, the ready state, that is represented by the green status LED. With the press on the on-off button outside of the room, the UVC modules are activated and we move to the active state. We introduced the blue status LED here to have a visual feedback of whether the UVC modules are currently turned on. Now, when we have a look inside of our UVC module, you can see that we added 2 devices there. One is the constant current source that supplies the UVC modules with a constant current of 450 milliamps. And the other one is the control unit, our power controller version 2, where we process all of the input signals, so the motion sensor signals and also the button signals are processed here. And according to these signals, we control the status and UVC LEDs. Now, in our previously mentioned room setup, the hardware setup could look like this. We have 4 UVC modules across the room, and the motion sensor is placed directly in the middle of the room. You can also see the button connections of the door and the on-off button at the bottom. And you can see that we have only one power control unit for that controls all of the 4 UVC modules. I previously said that there is usually one power controller per module, but since we want all of them to behave the same way, it is more efficient to use one power controller for all of them. Now, of course, this application is just one of many applications you could come up with. The other applications might come with different safety requirements. They might require, for example, less conditions, maybe a small disinfection box, probably does not need a motion sensor. But there might also be even more complex setups where we need more conditions, for example, additional sensors, a temperature sensor, a UVC sensor to make sure that there is no UVC light that makes its way out of the enclosed space. Fortunately, our products are highly flexible. The control unit can be adjusted to fit basically any scenario and any sensors there are. And also the LED module is customizable in terms of power output or layout and beam. Now, if you have any questions or projects you already have in mind, feel free to contact us. This is our contact data. And now I would like to hand over to Thomas Efsen.
Thank you. I need to get my screen. So, do you see my screen now?
Yes, indeed.
Very good. All right, so thank you for this opportunity to talk about the applications of UVC. In short, Efsen has 34 years of experience within UV. We do both curing and disinfection. And I think the interesting point in this is that in the curing, we have over the last decade been a part of the change from mercury-based and into the LED part of the curing area. And that's what we're seeing now also in disinfection, lagged by a small decade. But we do definitely see some parallels between what has happened in the curing and what is happening now in the disinfection with LED technology. We have a lot of knowledge in measuring and monitoring UV light, and of course we love making very nice systems. My colleague David has been part of this also. I think in the disinfection area we are mostly known for our handheld UV bar, and also we made this designer furniture which is a UV disinfection chamber inside. All right, so I'm going to try to give you 5 or 7 minutes into what an application builder's role is, and it is a very, very simplified description of this. Our role is to choose the most beneficial UVC generating technology source to the application our customers need. Among many things, we need to evaluate low pressure mercury versus UVC LEDs for the optimal source. So how does this start? Dose is the most important factor for disinfection. We need to reach a certain dose to get a certain disinfection. Our customers, most of the time, has a time constraint. So time is often the most important thing for our customers. It should be said that sometimes the time factor is not very high, and I'll get back to that. So how do we calculate the dose? We do that by taking the time versus the irradiance. And the irradiance is the milliwatts per square centimeter, or you will see it by watts per square meter. And if we go into the irradiance, how do we define the irradiance? Well, the irradiance is different from the source depending on the area that the source has to expose and how far that area is away. When we looked out into that, we also have to evaluate the price of the dose. So, you know, we can always add more LEDs and get to the point where we want, but it might not be a commercially feasible solution. So, I mean, picking the right disinfection source is not that easy, as you can see, but I mean, this is what experience lets you do. This slide, there's a lot of information on these slides, and I have a short time, so I'll go right into it. There's some of the benefits and disadvantages of low pressure and LED lamps, which we've heard before. I think the interesting thing is this graph. The blue graph is in irradiance of a low pressure mercury bulb at a distance. The red one is the same for the UVC LEDs we tested about half a year ago. And the purple one is the new UVC LEDs we just tested from Nietzsche. And what you see here is that there is quite a big step from half a year to now in the performance. And as these performance gets closer and closer to the low pressure mercury lamps, we believe that we will see LEDs taking more and more of the disinfection market out there. So what is the disinfection market? That is a big question. I mean, there's water, there's surfaces, there's air, and so on. If we just hold on a second. If we just look at surfaces, we have these different kind of ways to look at it. You will see that the axes here are logarithmical. So if you're very close, 1 centimeter, 10 centimeters, 1 meter, and 10 meters, and also the time that you have available to do the disinfection is logarithmical. What you see here is that a typical UV wand, as a lot of people are seeing out there, like our UV bar, there's also a lot of LED wands coming out there. They have both a place in the market. If you do not have a time constraint, the LEDs will work fine. If you have 20, 30, 40 seconds to disinfect a workstation, you could do with an LED wand. If you have less than that, a couple of seconds, you might want to go to a low pressure. So this graph, we think you can plot your products in and see more or less where does what source should you be looking at. The white area between the two graphs is what's supposed to be the gray zone. That's where the two technologies compete even more, and where prices get more even, and so on. What we expect to see in the near future is that the LED output and price performance will, the output will increase and the price performance will decrease. Hence, we expect this purple area to eat into the gray zone, making more and more applications preferably made with UVC LEDs. This one also, I'll bring the attention just to the status, what we see right now. LED UVCs are unique for small and narrow applications. It is the only solution. It is also currently being competitive, as we saw from Lumitronics, for large area surfaces where time is not a constraint. So if you have overnight for disinfection, LEDs might be the solution, but if you have to do it very fast in 5-10 minutes between the use of rooms, low pressure will still be the preferable one. LEDs will definitely grow more and more into the low pressure market as price comes down and performance comes up. This graph is our own little, you cannot base your future on it, but I mean, we are at about 27 to 30% of the irradiance of a low pressure today. If the development goes fast, I mean, we're probably there in a couple of years. If it goes slow, it's going to take a decade. This is more up to people like Nietzsche to answer this question. So Ray told that I was going to give a short information on bacteria and virus. I'll just say shortly that the SARS-CoV-2 that everybody's talking about needs a 10 millijoule per square centimeter for a log 3 reduction. And if we use an LED one there, we're looking at about 3.5 seconds in 10 centimeters distance, and about 1 second with a mercury source. Last slide before I hand over. When will we do things with UVC LED? I mean, we're looking a lot into it. We're testing a lot of it, and we're definitely believing that it's going to be a big part of the future. Right now, things like payment terminals, I mean, these small areas where compact shapes, yeah, UVC LEDs for sure. A UV wand like this, or a little cabinet where you can put in glasses or so on. I mean, we're just about to get there. I'm putting 1 to 3 years. It depends on the price performance. Our UV bench, if we want to put LEDs in that, it would require quite a lot of LEDs. Hence, it will be quite expensive to do today to get the time down to 10-15 seconds for a disinfection cycle. So, I mean, a good guess, 4 years, maybe a little faster. And for bigger things like, you know, these UV towers that blasts room with a lot of UV dose, I mean, that's going to be a little bit further out, but a good guess is between 5 to 10 years. So I hope I didn't confuse you more than enough, but there's a lot of factors affecting the right choice of source. Looking into LEDs is always our recommendation when you start a new application, so that at least you know when it's coming to you. Thank you very much. You're welcome to look more at uvcbyepson.com, and we're also available for the questionnaires in a second. Is that it?
Okay, thank you, Thomas. And thank you to all our speakers, very engaging. Right, let's tackle some of the questions that are coming in. A lot of questions about for UVC 222 nanometers. So I'm going to come to you, Thomas Westerhoff, first, and then I'll bounce it over to you, Jonathan.
Yes, 222 nanometers in far UVC is very interesting because you have currently the problem with 265 nanometers that the radiation, for instance, will get too deep into your skin, and therefore these wavelengths will damage the cells in the human skin. But there are researchers that show this, that with 222 nanometers, you will only affect the top layer of your skin where you have cells without an active core. They are dead cells and you can't damage them. But the problem of this wavelength is that it is technical, very, very difficult to realize this with LEDs. I know there are in our consortium, the Advanced UV for Life Consortium, some prototypes of LEDs with 230 nanometers available, but they have output powers of about 1 or 2 milliwatts yet. So I think it will take 2 or 3 years until LEDs in this wavelengths area are available on the market. So,
but all things being equal, Thomas, all things being equal, it would be a safe alternative, wouldn't it? 222.
Yes, it is a safe alternative because, but you have to keep in mind, as I said in one of my slides, at this wavelengths you will produce ozone, and you have to remove it because if you have an ozone layer on top of your radiation source, these ozone will also absorb a lot of the energy which you are producing. And if you have an LED with about 1 or 2 milliwatts and the ozone layer absorbs the energy, for instance, by a half, you only will have 0.5 or 1 milliwatt in result you can get onto your surface. But I think these wavelengths are very interesting for medical applications, like in surgery and so on. But there have a lot of science have to be done until it will get into the market.
Jonathan, did you want to come in on that?
I mean, I think Mr. Westhoff basically said the most of it. I think that there's currently a lot of studies when it comes to the effect of the 222 nanometer on the human skin. This might be beneficial over the classic UVC because this irradiation can come too deep into your skin layers as the traditional UVC can come. But then on the other hand, to make a LED like that and make it really beneficial for the medical market, I think we are way far away from that than having a reliable source in the UVC area, making the classic disinfection, I would call it.
Okay, and if anybody else wants to come in, don't forget, just put your hand up and I can see you. Another question probably for you, Jonathan, is people are asking about the lumen depreciation of UVC LEDs.
Again, what?
They're asking what sort of lumen depreciation do you get with UVC LEDs as compared to regular LEDs?
You mean the lumen?
Lumen depreciation. Well, I mean, they're talking. I presume they're talking about the, the degradation over time. It's not lumens we're talking about, obviously, but they're talking about, the
milliwatts. The milliwatts.
Yes. Sure.
Yeah. So I mean, in that field, we kind of are the company, I think, who can provide the highest reliability LEDs at the moment. You need to make sure, I mean, it's with lamps, it's the same. If you're using a lamp, you kind of make a specification that after a certain time you reach a minimum value, and this has to be there to ensure a safe disinfection. And the same way it goes with LEDs, you need to somehow define inside your application how long you want to use it. Usually, like lamps were just being replaced after a certain amount of time, and the same could be the thing with LED as well. But you need to be very sure about the temperature and all factors which can affect this reliability to ensure at the end of life, which you plan for your application, you still have enough dosage to make the disinfection you want to have make it work. And of course, therefore, we do this measurements as well. But this is just the measurement of the LED itself, and the real-time measurement needs to be done in the system. So we can just give you a reference of what our LED what it can do.
Okay, and somebody else is asking, what is the humidity withstanding of UVC LEDs? So how does it stand up to humidity?
Yeah, I mean, I showed a slide to that, and I think in general humidity is not good for LEDs. But we, for example, deliver in one of our packages, which I showed, the hermetic shield, which makes it drastically better in terms of reliability. But in general, humidity doesn't like LED.
Okay, good. Right, a lot of questions about your optics. Terob, I'm going to bring you in here. Let me see. First of all, what's again a similar question from a different attendee? What is the moisture proofing on the silicone optic?
Well, should I put it this way? It's enough to achieve ingress protection rating, but we do know that silicone microstructure is a little bit like a sponge, so there is it's somewhat permeable for example, water vapor. If we have a very humid environment and we have a long-term exposure to the silicone, then the silicone lens can permit a little bit of vapor to pass through the silicone. This effect is still, I would say, quite minor, and it's very heavily dependent on the thickness of the lenses. So usually it's not a problem in the real life application. But if you're designing a UVC disinfection lamps for the rainforest and some other greenhouses, some other similar places, then this is definitely one of the things that you need to take into account.
Okay, and Martin Bethel is asking a few questions about the silicon optic as well. First of all, can you estimate the transmission rate of your silicon in UVC? And then he says, how is transformed the absorbed energy? I presume what happens to does it become heat? And have you done any aging tests on the optic?
Okay, try to remember all the questions. So
the first
rate,
one's transmission rate.
Yeah, transmission rate close to 80%. So we are significantly higher than other grades of the silicon grades in the market. And what was the second one?
The second question is, what happens to the 20%? Is that energy absorbed as heat in the optic, or what happens to it?
That's correct. It's absorbed inside the lens and then converted into a heat. So if you have really high intensity application, this is definitely, again, one of the things that you need to consider when designing a luminaire.
Okay, and this final question is aging tests. Have you done any accelerated aging tests on the optic?
They are ongoing. So we have had this material now being tested for close to 2 years, if I remember right. And so far it seems to be doing okay. And that's a hardened test. So comparable real life exposure is, I would say we are somewhere close to 10 years at the moment. And some other silicon grades we have been testing now more than 5 years. LED was the first company who started to mold these silicon lenses in the past, so we have quite good knowledge about the materials themselves.
Okay. Simon Schwinger is asking the same question about lifetime. You've just answered this question. But he's also asking about the cost compared to glass.
We are more expensive, by some degree, but then again, if we remember my presentation where we were focusing the irradiation into the application, and if we can do that more effectively, if we can do optics which are doing more than just collimating the irradiation into certain area, let's say we can tilt the irradiation to face vertical surfaces, for example. In those cases, the silicone optics are significantly lower cost than comparable quartz glass optics. If the optics are something simple like, let's say, basic plano-convex lens that you can easily ground automatically in the machine, then those plano-convex quartz glass lenses are on par with the silicone lenses. No, they are actually lower cost. And then basic flat protective glass from quartz glass is, of course, lower cost. So depends very much on the case.
Okay, a lot of questions about the regulatory environment and controls and using UVC in areas where it's occupied. Now, Peter, I'm going to come to you with these. I'll just shoot through a few of them. First of all, Jörg Hannig is asking, how do you see the security requirements from authorities when using UVC in populated areas, occupied rooms? He says it seems to be more restrictive in Europe than in other regions of the world. People are asking about UVC in schools when they're unoccupied, and people are asking about, can you use UVC in rooms that are occupied, not directly, of course. So Peter, do you want to take that? Are we going to see regulations about the use of UVC in buildings?
That's a good question. I'm not sure if I want to answer that, if there will be regulations. But what I can say for sure, we saw some very bad examples in the past. In a kindergarten in China, I think that was one popular example that was very bad. And we all know that UVC light exposure can be quite harmful for human beings. So I think on a modular basis, with the solution that we offer, we can help to avoid things like that. But for sure, in schools, I think schools was one of the examples you asked. I think that we have different opportunities to ensure that nobody will be harmed. We can also in schools basically we can also have a disinfection of the air. I think Tero showed some opportunities with the LED lenses like this. So there are opportunities to have it in a secure way, I'd say.
Okay, Thomas Efson, if I could come to you. A lot of people, this question always comes up with UVC applications, and is there software where people can model this similar to, say, a Dialux or so, Relux or something like that?
Once again, if there is a...
Is there a software, where people can model UVC irradiation in space, or do you have to use standard like Dialux, Relux sort of platforms?
I don't think there's a software specifically that do take the full decision for you on what to use. I mean, I think you need to sit down and discuss with people that know about this stuff, how to do it correct. I mean, especially during the last 8 months in this pandemic, we've had a lot of approaches of people that want to integrate some kind of UV disinfection technology into their products. And it makes very good sense to think that way. But I mean, finding the right solution with LEDs or mercury-based or a combination is not just straightforward. And I mean, just going back to the topic that Peter just answered about regulations, it is a quite critical area, this disinfection technology with UVC. I mean, it is a wild west out there since the last 8 months. We see the market being, I mean, swamped with solutions that are really dangerous to be around. So do we see regulations coming in? I do hope we see it very soon. We need it to regulate this market, to keep the technology safe and well used. So, I mean, I mean, you can use our graph to plot in where you want to put your products and see what you do, but it's going to be changing all the time as the technology evolves. I hope that's an answer.
Okay. Number of questions too about any surface degradation issues with UVC, and somebody suggesting, does pulsating the UVC LED reduce surface damage? Peter, I'll come to you for that with that one.
Okay.
You get all the hard questions.
What was the question again?
Well, there's a number of questions talking about surface degradation with UVC, and somebody's saying, does pulsating or pulsing the UVC LED reduce the damage?
Can be, actually. I don't know. We didn't do any tests about that. I just referred to the article that was published in the UV Solution magazine. I think it can be an option because the optical power won't be as long on the surface, so that the damage will be less. Maybe Thomas Westerhoff knows something about that, but definitely we saw that there are some investigations right now to see how much the light exposure actually harms some surfaces, but I think this is an ongoing investigation at the moment.
Let's go to Thomas Westerhoff first, and then Thomas Efson.
Okay, yes. If you use a pulsed LED, you have to keep in mind that you have a duty cycle. If you have, for instance, 50% duty cycle, your LED is 50% of the time on and 50% off, and therefore the energy it emits is also the half and per time. And this may be the reason why you have a lower dosage on your surface over the same time, and therefore less damage.
Thomas Efson, do you want to add to that?
I think Thomas Westerhoff nailed it right there. It's again back to the dose. If you pulse it, you get half the dose and you get half the damage. I think the question might also refer to some pulsed xenon technology we've seen, or you can see out there for disinfection. I mean, this technology uses a lot of other wavelengths also. So there's a different effect on the materials there. I will say that UVC always has an effect on materials. The question is, how big is the effect, and does it matter for the user?
Okay.
And normally we say the effect is less than a physical cleaning of anything.
Of course, indeed, yeah, indeed. Interesting question. What is the impact of an ambient humidity of the efficacy of UVC and its ability to kill pathogens? So presumably people are talking about using it in, say, swimming pools and factories, restaurants, or anywhere where there'll be humidity. Thomas Westerhoff.
Yes, of course, humidity have an influence because if you imagine you have microorganisms, they have an optimal humidity and temperature range where their metabolism is very good. And for instance, you have an effect if you have very dry surfaces, then the lifetime of microorganisms, especially in bacteria, are lower if you have a dry surface. If you have wet surfaces, they will find, for instance, better conditions for living, and they will last longer on such surfaces. And these effects may only be a problem in air. If you have, for instance, high air temperatures above 30 degrees and high humidity, you will have a microorganism growth.
Okay, thank you, Peter. Gareth John is asking, what improvements do we expect to see in the efficacy of UVC LEDs over the next couple of years? What's the expected theoretical maximum radiant efficacy? That's you, Jonathan.
Yeah, and this is a question I expected, but of course it's hard to say. We can just say that we put a lot of effort, money, time, resources into that to improve that as much as possible. And we have some targets on our roadmap to go over this 3.6%, achieving 5%, achieving 6%. So it will go in steps. Like we cannot say next year we will hit the 50% mark like UVA LEDs, for example, or similar LEDs, but we will go there. We will go quick, probably a little bit quicker than Thomas showed in his presentation. I think we are on a good track to make a lot of things happen, but to give a really concrete value at how many percent we are, let's say in 2 or 3 years, it's kind of impossible today.
Okay, interesting question from Mike Ferrando. He's saying, is it better to combine UVA and UVC radiations or just UVC in order to achieve the best germicidal effect? Mr. Westerhoff.
Yes, we tested it in water disinfection system together with one of our partners, the Technology Center for Water in Karlsruhe. And we did some radiation tests with 265 nanometer LEDs combined with a 365 nanometers UVA LED. And there were no benefits that you have with a 365 nanometer LED. So a combination makes no sense. As I said in one of my slides, UVA can disinfect, but you need extremely high dose, about a lot of joules per square centimeters instead of millijoules per square centimeters. And I think currently it makes no sense to combine UVC with UVA.
Okay, and a simple question. I hope this might have a yes or no answer from Alan Tulla. Can UVC pass through windows? No.
well, it can if you have a very expensive slice of silica glass in your window, then it will pass. But normal glass, no, it doesn't pass.
Okay, it's opaque to it. Okay,
It's fully absorbed.
Fully absorbed. Okay, thermal management. Do we need heat sinks, cooling solutions for UVCs, LEDs in future? Peter Sonnenschein.
Yes, I think we do, but depends on the application, I'd say. It's hard to answer in general.
It depends how close you're putting them all, how much you're packing the LEDs in, how hard you're driving them, all that type of thing. Yeah. But could you see a time? Could you see a time when the efficacy improves where you won't need them?
Not yet. Not yet. As Jonathan said, it's hard to see where the efficacy of the solution of the LEDs will go. So it's hard to answer right now.
Jonathan?
Yeah, I think also when you're looking, for example, to like white LEDs, you still cannot drive them without taking care of the cooling. And they are pretty much at the maximum efficiency where you can go. The same with UVA. And then in the end, it depends totally on the design. If you need, for example, a passive cooling or an active cooling, of what kind of design you are going for. If you're going for a high array density of LEDs, which basically have 7 watts, like a UVC LED right now, and you just have 70 milliwatt of output power, basically the rest 6 point something watt is just heat, which you need to get rid of, and to make sure that your system is reliable. So is it possible to make it without cooling? Probably not.
Okay, a number of attendees are pointing out that I failed to spot your hand up, Tara, when you were asking about software. And we were talking about use of Dialux, and yeah, do you want to come in on that? Because you use, I don't know what software you use in your presentation for those renders that you had.
Yeah, actually, this is, I wanted to make a comment because this is something that we have been studying a lot and developing some processes, approaches, and considering that we can make, put lumen and milliwatts. They are pretty much the same thing if we forget that one is for humans and the other one is radiometric unit. And then milliwatts per square meter is pretty much the same thing as a lux. So considering taking these into, considering these, and you just switch the units, you can actually use Dialux for simulating. One thing that you have to do when setting up the Dialux is you have to put all the reflectances to the 0. So your room reflectances, etc., have to be at 0%. The software we were using for this upper air simulation is Visual Light. It's coming from 4D, company name 4D, and they actually have a module there which is designed for the UV calculations. So there you can actually calculate with the radiometric units. You can do all kinds of UV related simulations over there, and it can immediately you can set the dose ranges, for example, in that software, which will help you to evaluate which areas are having 3 log, which are having 4 log reduction.
Okay,
Yes.
thank you. That's really useful.
May I give some? Yes. May I give some addition? We at Fraunhofer, we do our simulations with COMSOL multiphysics. Well, it's an expensive product, but you have several modules. For instance, like the ray optics module, where you can simulate all the radiation problems. You have a CFD module where you can simulate the, for instance, water flow or airflow, and you have a particle tracing module where you can put some very small, some micrometer large particles in your airflow or water flow, and you can accumulate the radiation dose from your UV light source. And the good one on this software is you can combine all these different physics into one model, and this is the reason why we use it.
So just remind us of the name, Thomas. People are asking the name of the software.
COMSOL Multiphysics, COMSOL.
COMSOL, there you go. COMSOL. And finally, a number of people are asking about, oh, sorry, Tero.
yeah, this, okay, end of this dialogue after this comment, but yeah, COMSOL Multiphysics, actually we are using sometimes that one too, but we use it for different things, not for UV. Then ZMAX and SPIOS ray tracing softwares can be used for design as well. I just wanted to omit those, how should I say, professional ray tracer softwares and simulation softwares for their price tag, which is usually out of the reach of most of the common OEMs. Again, thanks.
Okay, useful. People are pointing out we talked about SARS, but we haven't really talked about UVC's effect on bacterial spores, microorganisms, mainstream stuff like that. Thomas Westerhoff.
Yes, you have several mechanisms how you can damage a microorganism. For instance, we said the main effect is the destruction of the nucleic acids of the DNA, which has a maximum of 265 nanometers. On bacteria which have a metabolism, you will also have a slight peak at 280 nanometers, but this is a different effect. It's a damage in the tryptophan, which you find in bacteria. And you can combine these two effects. If you combine a 260 nanometer LED with a 228 nanometer LED, I said in my slides, the wider the spectrum, the higher the efficiency is. But the 280 nanometer or the mechanism of tryptophan doesn't work in viruses. They don't have tryptophan. Yes. Is it?
Okay.
Is it answered or?
Yeah, I think so. Yeah. Right, quick question. I'm not sure who this is to. Mauricio Zanet is asking, what would be the best material to make a cover protection to a board with many UVC LEDs? Silica glass or silicone? Anyone? Hero?
For some reason, I would say silicone, and I think since you can do complex shapes with the silicone, and in its basic form, you can, if you just need to protect the PCB, then you can have compound cover with the silicone, and that you can just mold in your production. I would say that that's most flexible. In terms of performance or UV withstanding, in practice, there shouldn't be much differences between these materials.
Okay, another question come in for you, Tero, from Miguel Ferrando, who's asking, how do you demonstrate the efficacy of upper air germicidal ultraviolet disinfection?
This is still a concept which is running only in the simulations. We have done some luminaire example designs, but not yet realized the actual prototype for this luminaire, although we are planning to make one, and then we can actually measure it in practice. There is one study happening right now in the University of Helsinki where they are actually studying the spread of the bacteria and pathogens in the air, in the room air, and aerosol spreading of these pathogens, and we are planning to participate in that.
Okay, thank you, Tero. We're coming up to 11:30 GMT here in London, so we're going to wrap up. Lots of questions, and you guys have kindly offered to take a look at them over the next couple of days and pop some answers, so that nearly everybody who's asked a question will get an answer. And there's just too many, I'm afraid, to take them all today. But please, thank you to all our attendees for for asking our questions and giving us their comments and feedback, etc. That's really useful. I'd like to thank behind the scenes Charlie, Anna, and Niall for bringing together bringing our webinar together behind the scenes. Thanks to Nichia for making it happen and bringing together our speakers. And finally, just to thank all you guys, Thomas Westerhoff, Peter, Mario, Thomas Epson, Tero, and Jonathan. Thanks for sharing your expertise and your knowledge and your experience with us today, and all our attendees around the world. Thank you very much. And as I say, all attendees will get an email in the next hour or so, and there'll be a link there to see the recordings, and you can go back and look at the presentations, etc. in your own time. So thank you very much, guys. Thank you for your time today, and thank you to everyone for joining us this afternoon.
Thanks.
Thank you.
Take care.
Goodbye.